Good morning, and thanks for coming to my talk. The title of my talk is Robust Control Barrier and Control Lyapunov Functions with Fixed-Time Convergence Guarantees. This is the outline of my talk. I'll start with a motivating problem, then I'll introduce the notion of robust control barrier and robust Lyapunov control Lyapunov functions. I'll talk about how we can use these notions in a quadratic program-based formulation to design the controller, and will present a multi-agent case study. So the motivating problem is depicted in this particular figure here, where we imagine that these quadrotors are restricted in this green zone and are not allowed to fly over these red zones. So this part of the constraints constitute what we call as the spatiotemporal constraints, and this part is the spatial part of those constraints. Furthermore, for example, this particular quadrotor can be required to visit these blue regions in a given timely sequence, constituting the temporal part of the spatiotemporal constraints. And we need to satisfy these spatiotemporal constraints, or we need to complete these spatiotemporal requirements under input bounds or input constraints as well. So the problem statement that we consider here is how can we design controller satisfying the spatiotemporal constraints with under input constraints under various classes of disturbances. So the problem formulation is as follows. We consider a general class of control affine system perturbed by additive disturbance whose upper bound is known to us. So we do not know anything about disturbance other than its upper bound gamma. We also assume that we do not know the actual state x, but only an estimate of the state x given as x hat, and that the difference between the actual state x and its estimate is upper bounded by epsilon, and we assume that we know epsilon. We also assume that this x hat satisfies the similar equation or similar dynamical equation as the actual state x. We consider a time-varying or dynamically changing safe set given as a zero sublevel set of a time-varying function h subscript t. This is used to encode moving obstacles or other agents in a multi-agent scenario. So in particular, if agent I needs to maintain safety with respect to agent J encoded via this function h by having this h function being non-positive, then this time-varying dynamically changing safe set can be defined in this particular form. In particular, if the safety requirement is maintaining a safe distance of ds units, then the function h can be given in this form. And to encode safety with respect to all the other agents via single function h subscript t, we can use the approximation of the max function as the log sum x, and we can use this kind of an approximation to define a single dynamically changing safe set of this particular form. So to this end, we introduce the notion of robust control barrier function and robust fixed time control Lyapunov functions. Before that, we introduce zeroing control barrier functions as defined in the paper given below. So for a time varying set st, a function h subscript t is called as zeroing control barrier function if it satisfies this kind of an inequality for all points in the set S capital S subscript t. Similarly, we presented the following condition in the same session as this one today morning, where we showed that if a function hg satisfies this kind of an inequality for all points outside the set sg, which can be thought of as a goal set, then the system trajectories reach the goal set within a fixed amount of time. And inspired from that, the notion of fixed time CLF is defined in this following manner. So a function hg defining the goal set SG is called as fixed time CLF if it satisfies this kind of an inequality along the system trajectories for all points outside the goal set. So inspired from these two definitions, we can define the notion of first robust control barrier function. So function h subscript t is called as robust control barrier function if it satisfies this inequality along the system trajectories, where the difference from the control barrier function definition is introduction of this new term where L subscript t is the Lipschitz constant of the function h subscript t, and gamma is the upper bound on the disturbance. Similarly, using the notion of fixed time CLF, we can define the notion of robust fixed time CLF. So The function Hg is called as robust fixed time CLF if it satisfies this kind of an inequality along the system trajectories, where again, the difference is this new highlighted term where Lg is the Lipschitz constant of the function h subscript g, and gamma is the upper bound on the disturbance. Next, we show how we can use these notions in a quadratic program formulation. So consider this quadratic program where it is a quadratic program because the variables of optimization u, delta 1, delta 2, and delta 3 appear linearly in the constraints. And the constraints are explained here. So the first constraint is the input constraint encoding the input bounds on the system. The second constraint is the new robust fixed time stability condition for the goal set defined using function hg. The third inequality is for forward invariance of a static set S subscript S defined using function hs, and we use the robust control value function condition for that. And finally, for the dynamically changing set S subscript T defined using function H subscript T, we use the robust control value function condition to encode safety. Here, the head functions are defined in this particular manner. The highlighted term in the time derivative of these functions encode safety with respect to the disturbance d, whose upper bound is given by gamma, and the highlighted term in the definition of these head functions encodes, or rather are used to guarantee safety with respect to the state estimation error, whose upper bound is given by epsilon. All right, so this quadratic program is solved pointwise, and we use x hat in the constraint so that the closed loop control input is defined as a function of x hat. And so we do not need to know the actual state x, and we can define the control input as a function of the estimated state x hat. Let's see how we can use this quadratic program to solve a multi-agent case study. Before that, this highlighted term, which is the partial derivative of this function ht with respect to time, encode other agents' effect in a multi-agent problem. All right, so we consider autonomous underactuated underwater vehicles whose dynamics is given here, where x, y, and phi is the configuration vector, where x and y is the position, phi is the orientation of the agent, and tau ui and tau ri are the control inputs for agent I, where tau u is the control input along the x-axis, can be thought of as the thrust input, and tau r is the control input along the yaw axis, which can be thought of as the torque along the yaw axis. Here, to model the additive disturbances, we consider water currents whose magnitude and the direction both are assumed to be unknown. And we also assume that the system states are unknown, and we only know the system states within an epsilon bound. And we also consider input bounds on the individual inputs. So the objective for individual agents are given here. So each agent is required to reach a goal region within a user-defined time, encoding the convergence requirement. Each agent is also required to keep a point of interest pi in their field of view, highlighted in this green cone, defined using an angle alpha and a radius r. This encodes the static safety requirement for each individual agent. And finally, each agent is required to maintain a safe distance ds with respect to other agents, encoding the time-varying safety constraint. So this is a simulation video for four-agent scenario, where the green, again, the objectives include maintaining safety with respect to other agents, keeping the point of interest in the field of view, and reaching goal within a user-defined time. We are only showing the field of view for one agent, but every agent has their own field of views. The point of interest are given in the square dots, and the goal regions are given in the circular regions. As we see, as the agents come close to each other, they stop and they resolve their conflicts so that they maintain the minimum required safe distance, and each agent keep their point of interest always within their field of view, and eventually they reach their goal locations or goal regions within a fixed amount of time. So this figure on the right depicts the safety of the system where the function hm is pointwise maximum of all the barrier functions. So Hij encodes safety with respect to other agent, and Hr and Hp together encode the safety requirement for the point of interest. The three lines here, given in blue, green, and red, denote the three cases. Blue denotes the nominal case where we do not consider either the additive disturbance or the state estimation error. The green line denotes the scenario where we only consider state estimation error. And finally, the red line denotes error in the state estimation as well as additive disturbance. Finally, these are the closed loop trajectory plots on the left and the variation of Lyapunov function on the right, demonstrating fixed time stability uh, un, under the proposed control input. So to conclude, we presented the notion of robust control value function and robust fixed time control Lyapunov function to encode safety and convergence in the presence of additive disturbances as well as state estimation errors. And we demonstrated how we can use these notions in a quadratic program-based formulation to design control synthesis. Future work involves analyzing how we can resolve deadlocks for multi-agent problems. So here in this particular example that we showed, we consider 4 agents and we chose the initial and goal location in such a manner so that there is no deadlock among the agents, but a systematic way of resolving deadlock once the agent gets stuck into one still needs to be studied. Future work also involved using adaptive or learning-based approaches to reduce conservatism in incorporating robustness. In this formulation, if you remember, we use the worst case bound on the disturbance given by gamma. We can use adaptive or learning-based approaches to reduce conservatism by learning a form or something about the disturbance so that we do not need to use the worst case bound on the disturbance.